let's talk a little bit more about trees. So recall, a tree in the sense of graphs was a connected graph with no cycles. So what is a tree? So it's sometimes called a connected acyclic graph. And we looked at various examples of trees and tried to count trees, or at least by examples and so on. Now let's analyze how many vertices and edges trees can typically have. Okay, so I'm going to look at trees specifically in the context of vertices and edges. So if one sort of experiments with trees, so a tree on two vertices 1 and 2 can only have a single edge between them, right? Trees on 3 vertices, there isn't much we can do. I mean, there are many different labelings, but essentially this is all there is, just this path. And on 4 vertices you have this path, then there is this tree here. And observe, in all cases, here's an interesting observation, that the total number of edges, so if you count how many edges each of these trees has, so if there are 2 vertices, then there is only one edge. So there are 2 vertices but only one edge. In this case there are 3 vertices and 2 edges. This guy here has 4 vertices and 3 edges, and again this configuration is still 4 vertices, but still the number of edges is 3. And you'll notice this sort of curious fact, that no matter how you draw the tree, whichever configuration you pick, this is always true. Okay, so let's just try doing this with something like 5 vertices, for example. So I pick 1, 2, or maybe even 6. So here's a tree, and maybe let's make it even bigger. And now let's count how many vertices and edges we have. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices, and 1, 2, 3, 4 edges, 5 edges, 6, 7, 8 and 9 edges. Okay, so 10 vertices and 9 edges. And so this sort of suggests that maybe something like this is true in general, and let's state it as a theorem which says that a tree always has this property, that the number of vertices is in fact one more than the number of edges. Okay, but I actually want to go a little further than that. Let me state something slightly stronger than just that. So here's the theorem: let G be a graph, then the following statements are equivalent. Okay, so saying that the following are equivalent, so you've seen this before. So what this means is that logically one follows from the other, and the second statement follows from the first, and the first follows from the second, for example. And one can have the same thing with multiple statements as well. So let me make my statements, and then we will see how we prove them. So statement 1 says G is a tree. Okay, in other words, it's a connected graph and has no cycles. Okay, so that is the first statement. And we are claiming this statement is equivalent to the following statement, that given any 2 vertices of G, there exists a unique, meaning just one single path, there exists a unique path between them in the graph G. Okay, and recall, what is a path in a graph? It is a walk meaning a sequence of vertices, edges, reaching the next vertex, then following the next edge, going to the next vertex, and so on. And such a thing was a walk that we defined earlier. And a path is just a walk in which you don't come back to the same vertex more than once. Okay? You don't return to any vertex of the walk. So you have all distinct vertices. That's what a path was. Okay, so that's the second statement. Given any two vertices, you can find just a single path between them in the graph. That's equivalent to saying G is a tree. The third statement, which is also equivalent to these first two, is the following: G is a connected graph and it has vertices one more than the number of edges. So there's a cardinality of the vertex set is one more than the cardinality of the edge set. So let me maybe say that, let G equal to V comma E, meaning that's the vertex and edge set of G. So this is statement 3. Here's statement 4. It says G is acyclic, meaning it has no cycles, and the number of vertices is one more than the number of edges. Okay, so in particular, the statement, the observation we made that a tree always has one vertices one more than edges is really the implication 1 implies 3, if you sort of look at it, right? Because if G is a tree, then of course we know it is connected, and this statement is claiming that mod V is mod E plus 1. But this, in fact, this theorem actually says this is an equivalent condition. Just knowing that mod V equals mod E plus 1, together with the fact that G is either connected or it's acyclic, one of them is enough to tell you that G must be both connected and acyclic. Okay, so let's see how we would prove this statement. So before we prove this theorem, let's prove some intermediate lemmas, which are all interesting in their own right. So here's a little statement about graphs. If all vertices of a graph have degree at least 2, then of a graph G, then G contains a cycle. Okay, so recall what a cycle was. A cycle is just a path in the graph, meaning you follow various edges such that you don't repeat any vertices, except the very last vertex in the path is equal to the first vertex in the path. Okay, so such a thing is called a cycle. That was our definition. So the claim is that if every vertex has degree at least 2, then you will always be able to find a cycle in your graph. Okay, so let's prove this. So the proof is sort of a constructive proof as well, if you wish. So here's the proof. You start with any vertex of your graph, and you know it has degree at least 2. Therefore, it has at least 2 edges leaving it. Right? So pick one of them. So I started with some vertex, which I call 1, and I pick one edge which leaves that vertex, and I arrive at some other vertex 2. Now, having arrived at 2, here's what I do. I know that degree of this vertex, let's call these V1, V2 and so on, vertex 1, vertex 2. If the degree of V2 is at least 2, so let me call this edge as edge 1. Therefore, there exists another edge which leads out of V2, another edge meeting at V2, which is not the same as E1. Right? Therefore, there exists an edge at V2 which is different from E1. Okay, so let's call that edge as E2. Now what we do is we follow that edge next. So I go along E2. E2 is not the same as E1, so I don't go back to V1. Therefore, So I will reach some other vertex. Now, well, what happens at this point? I reach V3 and the degree of V3 again is at least 2. So I repeat the same argument now. Okay, so repeat the above argument to find another edge. Let's call it E3, which is an edge. E3 edge at E3 such that E3 is different from E2. Okay, so of course at this point it could happen that E3 is actually an edge which went back to V1. If it did, then I have already found my cycle. Okay, now if not, then I will reach some other vertex V4 and so on. Okay, so now you can sort of begin to see how this argument works. You reach V4, again since degree is at least 2, I will be able to find an edge which is different from the incoming edge and so on. Now I keep doing this, but the point is that the graph only has finitely many vertices. Okay, so you continue this process but graph G only has, the cardinality of the vertex set is finite. G has only finitely many vertices. Therefore, I can't keep visiting newer and newer vertices at each step. Therefore, at some stage, I must come back to one of the vertices that I have already seen during this process. So at some step, what should happen is that the new vertex that I find, Vn, must equal some older vertex, equals Vm for some m which is smaller than n. Okay, so the new vertex which I find, maybe until this point I keep finding different vertices, but maybe in the 6th step V6 ends up equaling V3. Maybe this is the 6th guy is just equal to V3. Now if that happens, what I've done is I found a cycle. So if has a cycle, well, it's this one here. Okay, so that's really the proof. So then observe that if you start at Vm, then you take the next edge which is Em, Vm plus 1, next edge m plus 1 and so on till you reach the very last guy. So the last edge was En minus 1 Vn. Okay, but Vn, remember, is the same as Vm. So this is a cycle. So this, recall, this was our notation for walks. So we would write walks as an alternating sequence of vertices and edges, and in this case it is a cycle because the last vertex in the walk is equal to the first vertex in the walk. Okay, so that is the end of the proof. So if you always have every vertex of degree 2 or more, you can just do this constructive process, and in fact this process will produce for you a cycle. It's not just showing existence. If you actually algorithmically follow this process, you will find the cycle at some point. Okay, so that is the proof of that lemma.